time. And I'm your host, Dr. Matthew Richardson, and welcome to another stream of CosmoQuest Astro Office Hours. Um, Give me a quick second to, make sure everything's running properly with Switch. My very last stream, I had to quit early because I had some problems with the connection, but things look to be going pretty well right now. All right, so let's see, Chrome. Switch. Go ahead and navigate over to CosmoQuest and see what's going on there. All right. It looks like things are going well, but let me first, as always, quit Chrome and reboot it so that I can actually access the chat. All right, there we go. And let's see who's all here. Hello, Susie. Hello, Electrical Skateboard. Hello, Michael T. Mayer. Hello, Peter. Hello, Tchaikovsky. And hello, WJM Tech. Welcome, guys. All right. So, the plan for today is to talk a little bit about, have a discussion on a question that was asked in one of the previous streams. So Larry, I'm unsure if he's actually here or not, but thanks, Peter. I'm happy to hear that the stream is going well so far. I hope it stays that way for the entire stream. But in one of the previous streams, Larry asked, I believe he asked, what happens to the gravitational force equation in the relativistic limit? Does it still hold up? And the quick answer to that is no, it doesn't. But today we're actually going to kind of get into the reason why it doesn't. Thanks, Susie. And so we're going to be having a little bit of fun with relativity today. General relativity, that is. All right. So I've been trying to think of a good way to be able to present this problem because of the type of math that's involved. So we're going to actually take this particular problem very slowly. And we're not actually going to talk specifically about the problem that was asked. That is, we're not going to attempt to solve for what would be the force on objects if one of the objects, the gravitational force between objects, if one of the objects is moving relativistically. We're going to take Einstein's field equation and we're going to attempt to derive the Newtonian gravitation law from Einstein's field equations. And we're going to go through this really slowly because I'm not going to lie to you guys. It's been a while since I've done this. I'm a little rusty. And that became quite apparent when I was going through the equations myself. So we're going to walk through this slowly, and hopefully by walking through it slowly, it will help me to make less mistakes, and it'll allow you guys to also keep up with the discussion. All right. So let's get to it. So, all right, I'm going to keep this screen up so I can see everyone's chat. All right, and I already started typing up some stuff, so I'm just going to slowly scroll through what I've done so far. And so we're going to start off with the problem of What is the Newtonian gravitational potential at a distance r due to a particle at rest in space according to general relativity? Again, this isn't quite the question that was asked in the past stream, but it'll help us understand how to approach that problem um, at the very least. All right, and so the conditions that we're going to require for solving this problem are the three we see here. One, the particle must be moving slowly. In our case, the particle is going to be at rest. Relative to our coordinate system, we establish the particle's at rest. Two, the gravitational field that's being produced by the particle must be weak. And lastly, three, the gravitational field itself cannot change with time. That is, in magnitude and direction, cannot change. It's static, it's constant. All right. So, hey Guido. And so we're going to go ahead and we're kind of just going to dive directly into it. And we're going to actually go through this equation and we're going to try to explain, I'm going to try to explain exactly what the equation is all about. So, Einstein's field equations are essentially summarized in the equation we see here. So I'm going to scroll down a little bit more so you guys can also read along as I talk about this equation. All right. So Einstein's field equation is defined as the Einstein tensor, which is on the far left-hand side of the equation. It's equivalent to time to make Matt hungry. Already there. It's equivalent to essentially this tensor object. So the best way in which I can describe tensors are you have to add some meat with that too. That makes this a soup really good. All right, but basically, it's a tensor. This R sub mu nu. It's called the Ricci curvature tensor. And what a tensor is, the best way in which I can explain it, is that it in itself is a geometrical object. It represents some geometrical object. Or represents a relationship between two or more geometrical objects. Then we can move on to the next term in the equation, which is this R, which is the scalar curvature. It itself is related to the Ricci curvature tensor. G sub mu nu is the metric tensor. And so basically this particular tensor allows us to be able to define the metric for our problem. And what the metric is, it's a way of being able to quantify the length between two events in a given space-time. G is simply just Newton's gravitational constant. C is the speed of light. And T is also another tensor. It's called the stress energy tensor. On the far right-hand side. So yeah, all you guys who are special like general relativity buffs, definitely chime in from time to time, because as I stated earlier, my general relativity is kind of rusty. But and T is the stress energy tensor, and basically it describes in so many words, it describes the energy, momentum, and stress for the system in question. It's all contained within that tensor. And so I've written here as a note that the left-hand side of the equation, that is the R sub mu nu minus 1/2 R G sub mu nu, basically deals with the curvature of spacetime. And that this spacetime curvature is brought about, and as we learned from, as anyone probably knows from general relativity, is brought about due to the fact that we have matter, right? Matter within our spacetime. And so that matter, or what's going on with that matter, is primarily going to be associated with what's going on the right-hand side of the equation. That is, we can describe the energy, the momentum, and stress that's associated with that matter distribution, or in this case, a single particle. Do not worry. I'm going to try my best to explain this very simplistic. I mean, if it's not making sense, let me know. Okay. And so what we're going to end up doing now is we're going to start with the right hand side of the equation, given the problem that we're trying to solve. And so the right hand side of the equation again is, let's see if I can highlight it a little bit. Okay, I can't highlight it. But basically, it's a constant, which is 8 pi g over c to the fourth times our stress energy tensor. So we can ignore the constant for the most part because it doesn't change. We're going to primarily focus on talking about the stress energy tensor and how we're going to use it for our problem. So the stress energy tensor is basically composed of 16 elements. It's a 4x4 matrix. And each of these components, or the components within this this tensor, this matrix, give different bits of information about what's going on with the matter within our system. So what I'm going to do now is I'm going to open up an internet browser, and we're going to navigate over to, let's see, there we go. We are going to navigate over to Wiki. Okay, it's there. Perfect. All right. So we're going to go over to Wiki, and we're going to see exactly how we should be looking at this stress energy tensor. All right. And so for the most part, we're just going to look at this image because pictures typically give 1,000 words. All right. And so let's make sure that you guys can see what I'm seeing here, though. Perfect. All right. So the very upper left-hand corner of the matrix, the component that corresponds to T00 represents the energy density times or divided by the speed of light squared. And so with those particular units, you end up getting just basically the mass density of your system, which in this case is just the mass density of a single particle. If the particle itself has some sort of momentum to it, then the linear momentum terms along the x, y, and z axes, which in this case, anything with a superscript in this case of 0, 1, or 1, 0 corresponds to motion along, or t superscript 0, 1 or t superscript 1, 0 corresponds to motion along the x-axis. T02 or T20 corresponds to motion along the y, and then T03 or T30 corresponds to motion along the z-axis. And what you'd put there is the momentum density of your system of particles, or in this case, our single particle. And then what you have within that inner 3x3 matrix within our stress energy tensor, so T11 all the way down to T33, that particular rectangle that you get from those two corners, primarily deals with mechanical stress that you're gonna have on your system of particles. Now, luckily for our particular problem, we honestly can ignore a lot of the components within this matrix. And the reason being is because our particular particle is at rest, therefore it has no momentum, and it's not undergoing any sort of mechanical stress. So for the most part, all the terms or all the components within this particular stress energy tensor matrix or tensor, excuse me, which in this case are one and the same, um, can be ignored, and we can focus strictly on the upper left-hand corner term, the T00 term. So let me go back. Let's make sure I'm not missing any questions here. So this is a 2 tensor. It's a rank 2 tensor. I'm so sorry, guys. If you have questions, by all means, ask. Um, yeah, this is a 2 tensor. So the typical way in which you can determine the number or the rank of a tensor is based off of the number of, how can I put, the number of indices it has. So in this situation, this tensor has 2 indices. All right, and I should actually make sure that that's right. I think it has a rank of 2. I feel confident about that. Let's see. Rank. Yeah, it's of order 2. So to go back to this, I've highlighted it there. Highlighted it here on the page. Okay. So now that we've kind of briefly explained what the stress energy tensor is all about, earlier I stated that the only component that will be important to us for this problem would be the upper left-hand corner, the T00 component. And so, and I'm realizing that there's going to be a lot of stuff that I'm probably going to have to explain because the location of where your superscripts or the location of where your indices are at, whether it's superscripted or subscripted, will indicate what type of vector or matrix it is. And so I'm going to get into that a little bit later, but for right now, just know that the T00 component is essentially the mass density of the system. And in this situation, it's just simply rho. That particular component is going to be rho. So if I scroll down, I've already put that in. All the other components go to 0. And we're left with a stress energy tensor in which it's only one component, and that one component is equal to the mass density of our system, which is composed of a single particle. All right. And so this is very important actually, because if we scroll up, and I even stated here, only one element of the stress energy tensor is non-zero, the T00 component, which allows us to focus strictly on this index, that is the 0, index, which on the left-hand side of the equation, and I'll just scroll up, on the left-hand side of the equation, the only particular value that we're going to be concerned with is the G00 component. So for values of mu equals 0 and nu equals 0, that's the only component we're concerned with. Now up to this point, math is not that bad. It's not bad at all actually. It's now where the math gets kind of a little bit more difficult. All right, so now we're moving over to the left-hand side of the equation, noting that we're only concerned with the 0, component on the left-hand side. But before we actually get into, trying to evaluate the Ricci curvature tensor and the Ricci scale or the scalar curvature, we need to establish what our metric tensor is going to be. And so again, remember guys, the metric tensor will allow us to be able to determine um, lengths in our space-time between two different points. All right. So I'm going to go back and make sure that I'm not missing any sort of comments here. All right. So I've kind of written out what I wanted to say in specifically, and that is we need to be able to satisfy the condition of having a weak gravitational field being generated by a particle. And so what we can do is we can take a metric tensor that is completely has no terms in it that will allow us to evaluate this weak gravitational field, and modify it slightly. And so it just so happens to turn out to be that the Minkowski metric, which is a flat space-time metric, takes into no consideration the gravitational field. However, what you can imagine, though, given that we have a weak gravitational field, is that we can take the Minkowski metric, which in itself describes or yields lengths between two events within our space-time, or 2 points within our space-time, and we can imagine that the weak gravitational field would cause small perturbations or small changes to the Minkowski metric. And all we'd have to do is just tack on another metric to the Minkowski metric to get this equation here, where our G sub mu nu is going to represent a curved space-time metric, which is composed of nu sub mu nu, which is, eta sub mu nu, which is going to be our Minkowski metric, which as far as we're concerned is simply going to be defined by, and I should probably bring that up so you guys can see it. Let's move back over to, let's move back over to our internet. Let's see, Minkowski metric. And so the equation that we want to use for our Minkowski metric, they have it here. Let's see. Maybe we might want to go somewhere else. I'm looking specifically for. Here we go. This is what I want. And so our Minkowski metric is going to be defined by the equation we see here. Can I highlight this? All right, it's not letting me highlight it, but it's okay. So ds squared is equal to negative c squared dt squared plus dx squared plus dy squared plus dz squared. And so what this equation is basically defining is, given 2 points in space, let's say some point S1 and some S2, in this case it's an infinitesimally small length between these 2 points, we can determine the length between those 2 points by essentially kind of using this equation that resembles Pythagorean's theorem, where we have one time component, which is represented by the first element on the right-hand side of the equation, negative c squared times d squared, and then we have 3 spatial components. the dx squared, the dy squared, and the dz squared. And if you wanted to be able to put this in like a shorthand notation or summation notation, it would be the equivalent of eta sub mu nu, which is the Minkowski metric, times dx dx superscript mu, which again earlier I was talking about the fact that whether the index is superscripted or subscripted, it means something. And so this particular notation is composed of a Minkowski metric that is represented by a covariant tensor, metric tensor. And by covariant, I mean that the index is in a subscript, and it's being multiplied by dx mu times dx nu, which in this case they're essentially representing the components of 4 vectors, and so but specifically they're going to be contravariant 4 vectors. All right. And then of course that's basically just the shorthand of what we're seeing in the center there. And if you actually wanted to be able to write out the Minkowski metric, it would look like this, where basically it's just the coefficients of our individual terms in the metric. All right. I really hope that everyone's able to follow what I'm saying here. All right, so I'm going to quickly take a run through the comments to make sure that I'm not missing anything here. One letter variable names. I'm not going to lie. At times, it can get very confusing with all these superscripts and subscripts and stuff like that. Also, one more thing I should mention. If an index, and I don't know if I can highlight this, but I can't. If an index is repeated more than once, that means that you're summing over that index, which is the reason why the shorthand notation expands to what we're seeing in the middle of the equation here. So the far right hand side will expand to what we see in the middle for this equation. All right, and we're gonna see that later on too as well. But I thought it would be a good idea to mention it now. Okay, I need. So yeah, so like in sub mu nu, if one of those subscripts, the mu or nu, is on another variable, whether it be in a superscript or subscript, that means that you're going to be summing over that particular variable. In this situation, our sums are going to always go from 0 to 4. I mean 0 to 3, excuse me. Where the 0 component is going to correspond to our time component, and components 1 through 3 correspond to our spatial components. To kind of show you what I mean by that, let me just go back, and I'm going to scroll down just really quickly, and I kind of define it here. So if we have a subscript I, and these are dummy variables for the subscript, so it could be just as well as mu, it could be j, k, whatever. Just note that the values for our subscripts will only range from 0 to 3. Nothing more, nothing less. All right. So, so to get back to what I was saying earlier, we need to be able to have a metric that will take into consideration a curved space-time. So we're going to have our Minkowski metric, which is basically the metric for a flat space-time, and we're going to add onto it a correction metric that will account for the perturbations or the small fluctuations or changes due to a weak gravitational field. I don't want to say fluctuations. That implies like the field is changing with time. Just changes due to the weak gravitational field. Let's put it that way. All right. And one more thing we're going to need to do though is, and this is what I was talking about earlier, we're going to now have to account for the fact that our curved space-time metric, which is going to be the variable g sub mu nu, we need to also take into consideration its contravariant matrix or tensor, excuse me. So the tensor I defined up here, I want to be able to highlight this stuff. The tensor I've defined initially, the g sub mu nu, is going to be our covariant metric, curved space-time metric, and the g superscript mu nu is going to be our covariant or contravariant, excuse me, contravariant curved space-time metric. And as you can note here, they have two different forms. And the reason why they have these two different forms is because when you take the product of the two, you have to be able to satisfy this condition here. Let's see if I can blow that up. So whenever you multiply the contravariant metric by its corresponding covariant metric, you get the Kronecker delta function or tensor. Is it a tensor? I think it's a tensor. You get the Kronecker delta tensor. I think it's a tensor. Where, and let me bring that up really quick as well. I'm sorry, this is a lot of information. I realize that this is a lot of information I'm kind of just throwing out here. So 0 is the 0th dimension time. Yes. In this situation, we're not worried about any higher order dimensions. 4-dimensional space-time. If we threw a 5th dimension in here, I'm not gonna lie, I have a problem with being able to explain what it is. All right, so my plan was to go ahead and show you guys exactly what this Kronecker delta symbol is all about. The symbol that's on the tensor that's on the right-hand side of this equation. So let me quickly go back to the internet. The internet is our friend today. So we're going to go ahead and we're going to type in, I hope I spelled this right. There we go. All right. And so the type of Kronecker delta that we're working with is considered, I believe it's a mixed one, mixed index. So let me find that one. Here we go. And so essentially, you have two conditions for this particular tensor. And the two conditions are if I and j are not equal to each other, the tensor is equal to 0. However, if I and j are equal to each other, the tensor is equal to 1. And I mean, it's probably the simplest tensor that you could possibly deal with in relativity. Very simple and straightforward. And no matter what type of form of this tensor you're dealing with, this will always be the condition. If I is equal to j, the tensor is equal to 1. If they're not equal to each other, the tensor is equal to 0. All right, so let's go back. All right, so all this information is very important for us being able to solve for what we're going to move into next, which is the Ricci curvature tensor. Now note, everything we're focusing on now is on the left-hand side of Einstein's field equations. All right, so what I'm going to do now is I'm going to go over to back to Wiki, so we can quickly talk about what this Ricci curvature tensor is all about. Hey, keeper of maps. I'm sorry, guys. Again, guys, if I'm not making sense, let me know. All right. So, okay, if that's the case, I'm going to try to move through this a little bit more slowly. All right. So going back to the internet, we're going to talk a little bit more about this Ricci curvature tensor. Let's see if this gives them a good. Now, to kind of basically explain this, we need to first define what this term geodesic is. And so, if we could imagine a flat sheet of paper. Actually, do I have paper here? I might have some paper here. I have some paper. Let's take out one sheet of paper. And I pray that you guys can see the lines on the paper. So I have a sheet of paper here, all right? Let's make sure that you guys can, let's get it closer. Perfect. Have a sheet of paper here. Along the surface of this paper, there are straight lines. But each of these straight lines could represent a geodesic. Its very own geodesic, which is basically just a line in some space. In this case, our space is flat, and it's a straight line. But if we could imagine that we were to start bending this paper in such a way that we were making it into a sphere, well, according to our view, the line would not be straight. But you can have straight lines in in higher order dimensions. So a good example of what a geodesic would be in a curved space-time, or like for example with a ball, is lines like longitude and lines of latitude. Those themselves would be considered geodesics. They're straight lines on a curved surface. And so this Ricci curvature tensor, what it allows us to do is be able to measure exactly. It allows us to measure how far off we are from a straight line on a curved surface when considering the curved surface in like the Euclidean space, which essentially is the three-dimensional space that we know of in terms of Cartesian x, y, and z. So if we were to imagine a ball and we had lines, that is geodesics along this ball or on this ball, what the Ricci curvature tensor would allow us to do is exactly measure how much those lines deviate from being a straight line. So for example, if there was like a little hump on the ball, the Ricci curvature tensor will allow us to measure exactly how much of a hump there is. Sounds zen. At least that's my understanding of the Ricci curvature tensor. For all of you guys here who, like I said earlier, are just like really, really good with general relativity, if you guys have a better explanation, please, by all means, like drop it into the chat. But that's basically my idea. That's been my idea of how I understand the Ricci curvature tensor. All right, and so we're actually just going to scroll down on the same page here because it should have the equations. The equation that we're going to want to be able to use for determining the values of the Ricci curvature tensor, excuse me, is given here. Let's make sure I'm cutting off exactly what I don't want. All right, that's perfect. Where the Ricci curvature tensor R sub out, in this case alpha beta, and again we can change these indices to whatever variable that we want. But R sub alpha beta is going to be equal to, and I'm going to skip that that second, the middle equation there, and go right to the ending equation here, which is the partial derivative, or the Roth partial derivative of what's known as the Christoffel symbol. And I'm not going to go through every single, there's 4 terms here, where 2 of the terms are going to be partial derivatives of our Christoffel symbols, and the last 2 terms are basically just products of 2 Christoffel symbols. So note already here though, we're kind of getting into partial differential equations, and it's for this reason that it's for this reason that being able to solve the original problem that the Larry asked a while ago about what would happen if the particles, what would happen in the relativistic limit for gravitational force. It's because of these partial derivatives that it makes the problem so much harder. In fact, if I'm not mistaken, we're going to end up getting into second order differential equations because the Christoffel symbols themselves are also partial differential equations. And so you're going to end up getting second order differential equations, and some of them will be nonlinear, meaning that we're not going to be able to directly like have an analytical solution for them. So this is the reason why I've chosen just to go over this particular problem, because there is an analytical solution for it. And the analytical solution is Newton's gravitational force equation. So, no, Larry, no need to apologize. Not at all, not at all. It was a great question. It was a great. It kind of like threw me for a second. It was a great question. It was actually a very simple question. It's just that the answer to get to the answer is very complicated or complex to get to the answer. All right. So this is our Ricci curvature tensor. And so now we need to be able to understand exactly, to solve that, we need to be able to understand exactly what these Christoffel symbols are. And you know what, guys? I don't think I'm going to really get into any math today because, or at least any like derivatives just yet, because we need to kind of understand exactly what these things are. So I'm just going to open up another link that kind of goes over the Christoffel symbols. And I'm not going to lie, guys. I'm going to be very honest with you. A physical explanation of the Christoffel symbols is very difficult for me. If you want, you can be able to just look at this page and kind of read through it to see if you can understand it. But when I was taking general relativity, I could never get the physical understanding of these things. Um, but nevertheless, see if I can find it. Here we go. And so the Christoffel symbols that we're going to be dealing with are the Christoffel symbols of the second kind. And so the equation that's going to be most relevant for what we're going to be doing is here. So I'm going to scroll or zoom in. And so the tricky thing about when you're dealing with these Christoffel symbols is that even earlier I mentioned that if you see an index, if you're looking at one side of the equation and you see an index and it repeats itself, that means you're summing over that index. So in this case, on the left-hand side of the equation, I'm seeing we have a gamma with the superscript I. Let's make sure you guys are seeing what I'm seeing. Perfect. We have a gamma with a superscript I and a subscript KL. And so we're going to actually just choose what those values are. And again, whether it be I, K, or L, the values that they can take on are either 0, 1, 2, 3. 0, 1, 2, or 3. But if you look at the right-hand side of the equation, we introduce this new variable m. And the variable m is not defined on the left-hand side of the equation, 1, and it repeats itself on the right-hand side of the equation, 2. So it turns out that that's the variable that we're going to be summing over. And again, we're going to be summing over each of our coordinates, which is one time coordinate and 3 spatial coordinates. So 4 coordinates altogether. So the terms that we see here, there are a lot more terms than what we physically see in this equation. And I just know that when I first started off doing this stuff, that was the one thing that I could never get. And I always used to get my solutions wrong because I was missing terms. And it's easy to miss terms too, if you're not careful. Okay. That is enough talk about that. Go ahead and check the comments really quickly. I'm sorry. Oh, excuse me. I'm looking at Larry's comments here. Are Maxwell field equations this hard? Maxwell, there's 4 of them. No, no, they're not. No, at least in my opinion, they're not this difficult. I mean, the real difficulty here is keeping track of all the terms. This notation can really fool you because, like I said before, you're summing over some of these indices. You're summing over them, and you can easily miss a term or two. So this equation is important, and there's one more bit of information on this page that's also important. So I'm going to scroll out, and that would be this. This is very important in dealing with Einstein's field equations because you're going to get a lot of these gammas. And it just so happens that if you run into a gamma or 2 gamma values that are in different terms that resemble what we see here, that is the superscripts are the same, but the subscripts are interchanged. They're basically the same. They're the same gamma or the same Christoffel symbol. And this is just due to the nature of how the Christoffel symbol is defined. And so if you run into situations like this, you can actually cancel out terms that have Christoffel symbols that are similar, like this. But then again, even if you didn't cancel them out in the beginning, once you solve for what the Christoffel symbol is actually equal to, you'll end up seeing it cancels out anyway. But it helps cut down on time when running through these equations. Larry, oh man. I can't help but laugh at what you're saying. I'm sorry. Zooming in does not make it clearer. Kind of like raising your voice and speaking slower to someone. Sorry, guys. Yeah, we're gonna actually put some of this math into practice. And thank you, Keeper of Maps, for explaining that to Kings of Wizard. Welcome. That is a new name. But let's move on actually, and I'm going to try my best. I'm going to try my best to make sure that no, I really should try my best to make sure that I'm explaining this stuff clearly. Um, and if I'm confusing you guys, I do apologize. That is not my intent here. I just want to be able to kind of get at the question that Larry asked a while ago. All right, so let's move back. We're gonna go back here, and I've kind of already started a little bit of the problem, and I decided that I would actually walk through the terms the best that I could. All right, so let me pull up my tech document and actually kind of scroll down here. So really, all the information I just covered was probably about a couple of weeks of general relativity, and I know that I'm not doing this topic justice, um, but I really wanted to be able to get to the solution, and we're probably not even going to be able to get it done today. I'm pretty sure of it actually. So we're going to pick up with this wherever we leave off. All right. So again, earlier, guys, I was stating that on the left-hand side of our Einstein field equation, I'm just going to scroll up here. On the left-hand side of the Einstein field equation, we noticed, and again, or the right-hand side, excuse me, the right-hand side being 8 pi g divided by c to the fourth times the stress energy tensor. We noted that for the stress energy tensor, that all the components go to 0 except for one, and that component being the row in the upper left-hand corner. Well, given that we only have one single component with a non-zero value, the same is going to be true for our G sub mu. It too is a 4x4 matrix. It will have components that are going to be based off of whatever the values are in our stress energy tensor. And so given that our stress energy tensor has one component with a non-zero value at component 0, 0, our G sub mu matrix will also have a non-zero value for that component, and everything else will be 0. It just so happens that if you're dealing with vacuum, all your elements are all your components of your stress energy tensor are going to be 0. Therefore, your Einstein tensor itself will also be 0, and there won't be any need to actually like solve any of these equations. All right, so again, we're dealing with the G00 element, which in itself corresponds to just only evaluating the Ricci curvature tensor at the 0, 0 element as well, or component as well. So what I've done is I've taken the equation that I was showing you on um, the previous Wikipedia page, and I've essentially just plugged in my 0, 0 elements, and then everything else that's left over, all the indices that are left over, are indices that we're going to be summing over. So in this case, we're summing over two indices, rho and lambda. And there's one more thing to note. As a result of the fact that we've assumed, or not assumed, but we're forcing the condition that in this particular limit that the field is static. That means all time derivatives must be equal to 0. So nothing should change in time. And so now we can actually figure out what our Ricci curvature tensor reduces to. And there's also one more thing we could do, but I want to work out through all the terms and see if that's what really happens. Given that we're also applying the constraint that our particular system is or the region that our system is going to be defining is only has a weak gravitational field in it, we can also even get rid of the last two terms in our Ricci curvature tensor. But I want to see what happens if we actually try to evaluate everything. Do they just naturally cancel out, or do they just become negligible because like they're really small values? All right. Actually, guys, I think I'm going to leave it at this, and we're going to definitely pick up this for our next stream. But quick question, and be brutal with me, guys. How was the explanation? If it was like completely out of the water, like let me know. I should be watching the comments. Yeah, I know who you are. Oh, I see now. Flash, Flash Gordon. But yeah, what did you guys think so far about the discussion? Hey, Shogun's King. I apologize that you missed most of the discussion. But yeah, basically we're just using yeah, it's a lot of information. I swear when I took GR, I mean, we spent at least half of the semester, going over like all the types of like the notation and stuff like that, trying to understand exactly physically what these tensors are actually telling us about 6 hours. I keep forgetting that's right. Like it's fairly late there where you're at. Yeah, I'm with you, Shogun's King. It's been a while for me too. Oh, oh man. Ah, yeah, I know, Adam. That's kind of what I was worried about. Because, like I said earlier, I mean, like many of these equations we covered over at least like half the semester, and that's even with being able to like go home and do like work through like problems and stuff like that. So what I'm gonna do is I'm gonna see if there's a way of being able to write things up and just post it to the weekly Space Hangouts Slack. That way, you guys can like kind of see where I'm going to be going. Honestly, the math itself is not that bad. It's like yes, all the symbols and how indices are like thrown around in here is it's insane. And just in case we need to be able to refer to things, I made a glossary to kind of like be able to keep up with a few things. And might keep adding on to it as we move on. Yeah, I agree with you. So what I'm gonna do is I might write like a little explanation in the glossary section. All right, guys. Well, the time's now 1:02 p.m. and I hope you guys enjoyed the discussion so far because we will be picking it back up next Wednesday. Um, but thank you guys for like stopping by. Okay, I'll definitely do that keeper of maps. All right, guys. I'll see you guys next week, Wednesday, 12 p.m. Central Time. All right, bye. Yeah. Um, this particular metric is a combination of the Minkowski space metric and um a correction metric. All right, that's it. I'm gonna log off now. Okay, bye guys.